Constantine, Tobias Fritz, and Paolo Barone, which has been on the archive for a bit, but just went up in more modified form, 2 papers, which I'll give links to at the end. So the general idea, I'll start with a hopefully uncontroversial statement, which is that algebra is all about evaluating formal expressions of one kind or another. So the most basic kind we're used to is you have something like 1 + 2 + 3, and we know that that should evaluate to 6, but you could just do that, once one and done all the way there, but instead you might want to partially evaluate it to 3 + 3 along the way to 6, or you could go to 1 + 5 instead if you prefer. And we have rules about how we always get to the same place. And what we study is how you can actually add higher dimensional structure to this picture. So I'll show you what it means to fill in these triangles and even add higher dimensional cells to a drawing like this. And the motivating question in doing this is, do these partial evaluations satisfy the axioms of a category? And if not, how close can they get? What sorts of compositional structure do we have here? And so before getting into that, I'm just going to introduce some notation about monads. So I'm not going to fully explain what monads are, but hopefully this will give some sense of how we're going to think about them, even if you haven't seen it. So we start with a monad on sets and say X is a set with variables like A, B, and C in it. And we want to think of elements of Tx as formal expressions on X. So if our monad sends a set to the free monoid or free commutative monoid on that set, those formal expressions could look like these. You could just have A or B + B or A + C + B. But the notation I'm introducing is we're actually going to draw little boxes around the variables when we write formal expressions with them. And it'll hopefully become clear in the next few minutes why we might want to do that. And then in keeping with that, we can write elements of t to the n of x as nested formal expressions, where t2 of x, for instance, we have these sums with 2 levels of boxes around them. So, and you can add things either inside or outside the boxes, or except for the innermost boxes, but I'll get to that, I promise. So, and for t3 of x, you would have 3 levels of boxes and so on and so forth. And so we'll see a little bit more about how this works. But first, I want to introduce another monad as an example called the distribution monad, where the formal expressions are convex combinations of the elements of our underlying set. So in this case, you could just have A, or 1 times A, which I probably should have written, or a third A plus 2/3 B. The point is that they have to add up to 1. And so this monad relates to probability. And this is a good chance to illustrate some of how this notation works, where the unit for our monad, for every element A of our set X, we get a formal expression just by drawing a little box around it. And for this monad, we also add a coefficient of 1 to the outside. For the free monoid monad, you wouldn't. You could just have A in the box. And the multiplication for the monad, where if we start with something in TTX like this, so we have a convex combination of convex combinations, where we have coefficients on both the inside and the outside. The multiplication for the monad is given by erasing the outermost boxes and then distributing the coefficients, reordering the terms. And you can check that this doubly nested expression gets sent to this single nested expression after doing that. And so this is part of why we like this notation, because the multiplication is just removing outer boxes, unit is just drawing a box around the outside. And we get some even nicer things later on, which we'll see. And so we can also sort of use this example to describe a related one of the free S module monad. So when we define this distribution monad, all we really need is coefficients, in this case given by these fractions, which can be added and multiplied together and maybe have a unit, like 1, for defining the unit of the monad. And so all we really need is a semi-ring. And we can drop the condition that they have to add up to 1. And so you could then reinterpret this as what we see on the screen now. We could reinterpret these expressions as those for free S modules, where S is perhaps positive real numbers. And then when we're talking about monads, we'll also often consider algebras, where we have a means of, like I said at the beginning, evaluating formal expressions. And so the way we picture this in the notation is if we have a formal expression over an algebra, like the natural numbers, or an algebra for the monoid monad, then the evaluation is interpreted as removing the boxes. And so this has the convenient property that 1 plus 2 plus 3 does in fact equal 6, and we don't have to worry about whether we're considering them as formal expressions or just elements of our set of natural numbers. So that's a convenience which we take advantage of with this notation. And we'll also see that this gives us some nice interpretation of some other nice maps we get. So I'm going to mention one other algebra before I move on, which is the trivial S module. So this is the S module with a single basis element, where I've just written that element of the singleton set as star. And elements of the free S module on the singleton set are just given by some coefficient in our semi-ring S applied to the only basis element. So that's in S, and then when we evaluate a formal expression like this, it just goes back to the basis element. We don't have any choice. And this may seem like a rather boring algebra, but we'll see that it actually provides an interesting counterexample in a few minutes. So, all right, that's a little bit about how monads and algebras work, and I'll keep showing the notation. But now we want to talk about partial evaluations. How do we give a formal definition of these things? And all I'm going to define a partial evaluation as is just a single doubly nested expression in T2a, TTA. So if that expression is called V, it's just, in this case, a sum with 2 levels of boxes drawn in. Then we can define the source of the partial evaluation, which here is written as P, by applying our multiplication, removing the outer boxes. And you see we then get 1 plus 2 plus 3 plus 4. Whereas the target applies TE. So I didn't mention it before. If E removes the only boxes of a formal expression, then TE can be interpreted as we remove the boxes inside one level of, I guess, formality. So that would be the inner boxes in this doubly nested expression. So a partial evaluation has 2 levels of boxes. The source removes the outer ones. The target removes the inner ones. And this hopefully is vaguely consistent with what you expected a partial evaluation to be, at least when we're talking about sums. And then we can draw in some other ones. You can always draw a box around it and evaluate to just a single element like this. And this picture perhaps suggests, can we compose these things? Is this triangle we have here a composition relation in a category, perhaps? Is that something we can do? And in general, the answer is no. And I'll show you why. So I'll just keep a definition of partial evaluations at the top. And in our trivial S module, the second algebra I mentioned before, we can write out a general form for these partial evaluations, elements of TT star. where in particular, an element of T star is just some R1 or Rn applied to our single basis element. And TT star is then the free S module on those. So in formal sums with coefficients in our semi-ring S of these module elements. And we can then check what the source of this partial evaluation is. We remove the outer boxes, and that gives us this sum of products. And for the target, we're going to remove the inner boxes, which, if you remember the evaluation strategy for this algebra, it just removes this coefficient R. It sends what's inside these outermost boxes to star. And so we forget the inside coefficients. And those are all of our partial evaluations for this algebra of this particular mode. And so I can now give you a choice of semi-ring, namely the natural numbers adjoined root 2, which have the form of a natural number plus some natural multiple of root 2. You can check that they're closed under addition and multiplication. And we then can start just drawing some partial evaluations. So in this case, by putting a 0 on the inside, which gets forgotten when we take the target, but remembered when we take the source, we can partially evaluate from 1 to 2. And then we can further evaluate to square root of 2 applied to our basis element. Remembering, if we forget the outer box, then we multiply these and get 2. If we forget the inner box, then this goes away and we just have the square root of 2. Except we would hope that we can compose these and get a partial evaluation directly from 1 to root 2. And if we want to do that, we can start by just writing in our general form. We want the target to be root 2. So we get this equation in our semi-ring S. Except this is very restrictive, because since we don't have any negative numbers, we only have natural numbers and natural multiples of root 2, there actually aren't very many options for what this sum can be to add up to root 2. And in fact, it has to be a single copy of root 2 and nothing else except zeros, which don't count. So that lets us reduce our options for this partial evaluation significantly. And then we also expect that the source will be 1. And so we forget the outer box, we get root 2 times R1, and we want that to be 1. But that's not going to work, because root 2 is not invertible in this semi-ring. 1 over root 2 does not have the form given here. And so this tells us that we're not going to have a partial evaluation from 1 to root 2, despite having 1s from 1 to 2 and 2 to root 2. And so this is one of our main results, that partial evaluations do not generally compose. And so this is when we start introducing the higher dimensional structure and see what we can do without knowing we don't always have composition. So we're going to describe a simplicial set called the bar construction of a T algebra. Now, and the end simplices are going to be these nested expressions. So if you've seen simplicial sets before, this picture might be familiar. But if you haven't, feel free to ignore that. What I really want you to think about is this one here, where we have this triply nested expression in the middle. And if we forget the outermost boxes, we get this one here on the left. If we forget the second level of boxes, we get this long one on the bottom. And if we forget the innermost boxes, we get this one on the right. And indeed, you can check. Here you just keep 1. Here you get 2 plus 3, that's 5. And here you still have 4. And if you add additional levels of nesting, you get higher dimensional simplices, which obey similar relations. And it's actually rather nice to check that the simplicial relations hold just by removing the boxes. That's a neat property of this notation. So what can we say about the compositional structure? For some monads, we always have a category. So the free monoid monad that I've drawn previously, but also free semigroups, the free M-set monad, whose algebras are sets with an action of a monoid M, or a group action if you prefer, is the nerve of a category. So for group actions, it's the action groupoid. Monoid actions have an action category. And there's fairly nice descriptions for monoids and semigroups as well, which don't have as catchy names. But we want to consider more general monads usually, and more general operads. And for symmetric operads, we don't have this. So the free commutative monoid monad, our constructions of its algebras are not generally categories. And an example of this, which unfortunately I won't have time to draw out, is that the bar construction of the commutative monoid of natural numbers is not only not a category, it's also not a quasi-category. And if you're not familiar with quasi-categories, this is just a weaker notion of category among simplicial sets, which homotopy theorists are especially fond of. But what are they? So our positive result is that these bar constructions for symmetric operads, but also the distribution monad and a more general class of what are called BC monads that I won't get into, have this property called inner span completeness. And so what do I mean by that? If we have a simplicial set, it's just a diagram of points, edges, triangles, and higher dimensional cells, like what I've drawn before. And we have a subdiagram of it that looks like this, with two simplices which share a boundary simplex. So here they share an edge. Then we can always fill that in to get an entire simplex. So if we have, in this case, two doubly nested or triply nested expressions of this form, which agree in the appropriate doubly nested expression, we can always construct, perhaps not uniquely, I guess this would be a 4 times nested expression. And so we have this lifting diagram for all maps from this, which is just this, into our simplicial set. We can always extend it to an entire simplex. But we can make this. We can give a different formulation of this, which is, I think, a little bit more helpful. Forgot to mention, we can only do this for inner spans, which contain this entire spine of, in this case, 3 sequential arrows. There's a maximal string of arrows in each n simplex, and here there's a missing edge, which is actually one of them. And that precludes us from doing the lifting. So we can only do it for inner spans. And so I'll finish up by mentioning that we can actually fill a more general class of diagrams in these bar constructions into entire simplices, which is going to help us with compositional structure. So we call these diagrams directed acyclic configurations. So like I mentioned before, they need to contain the spine of the simplex we're hoping to fill to. Their one skeleton, which means their vertices and edges, needs to be a chordal graph. So if you have any cycle of length greater than 4, where we ignore the directions of the arrows. So this is a 4 cycle despite the strange directions. And it has a chord, which means an edge cutting it up into smaller cycles of length 3 eventually. And then any simplex boundary, for instance, a length 3 cycle, which bounds a triangle, can be filled in. So in this last picture, it was hard to draw in a helpful way, but I want you to imagine that this back face and these 2 front faces are included, and this bottom face with the dots in it is not included. So we call that a horn, which is the homotopical terminology. That is not a directed acyclic configuration because it has this 2 simplex boundary down here, this triangle, which is not filled in. So horns don't satisfy this, but the spine inclusions do. So if you only have a string of arrows, here it's length 3, but it could also be length 2, including into the 2 simplex, then you can always fill that in to, in this case, a 3 simplex, and then take the long edge, this one here in the back, and that gives you a composite. And it's not going to be unique, but we have some higher structure, even if it's not especially strong, like in categories where we do have uniqueness. And so I'm gonna stop here for the sake of time, but the last thing I was going to mention is that we can, these conditions are inspired by database theory, where if we have some table with attributes A, B, C, and D, then if we want to split that up into smaller tables, perhaps to remove duplicates, there are no duplicates here, but if these attributes were like customer name, customer city, and customer state, you could maybe keep track of what state each city is in without copying those entries for every customer. We want to know if you might be interested in knowing if you can reconstruct the original table from the ones like this. And in this case, you actually can't, because you can check that 0, 1, 3, 4, which is not in our original table, does fit these tables, because 0 and 1, the first two, the A and B entries, are in this table. 1, 3 is in this table, and 0, 3, 4 is in this table, albeit coming from different entries of the original. And so that's not a desirable property of a collection of tables. And you can check that if you treat these tables, so if this original is the entire 3 simplex, the simplex on 4 vertices, and these tables are we can treat these tables as a configuration of this, and we would want it to be acyclic in order to have this property. Anyway, I will stop there. Thank you very much. And here are some of the references.
Thanks, Brandon. We can